Hello and welcome. Tonight we are going back to a quiet desert morning in July of 1945. A morning before sunrise, a morning before the world had ever seen a nuclear explosion. In the darkness of the New Mexico desert, scientists, soldiers, engineers, guards, and observers waited for a test unlike anything in human history. They had built a device they called the Gadget. It was a plutonium implosion bomb assembled by the Manhattan Project after years of secrecy, calculation, uncertainty, and fear. The test was called Trinity. It would be the first detonation of an atomic bomb. And before it happened, before the fireball rose, before the desert sand turned into green glass, before the nuclear age began, there was a question so strange and terrifying that it almost sounds like myth. Could the bomb start a chain reaction in the atmosphere? Could one explosion ignite the air itself? Could the first atomic bomb burn the sky, spread through the atmosphere, or even destroy the world? The answer, after calculation, was no. The atmosphere would not ignite. The oceans would not burn. The planet would not be consumed in a runaway nuclear fire. But the fact that the question had to be asked tells us something important about that moment in history. For the first time, human beings had created a device that reached into the forces at the center of matter. They were no longer working only with fire, pressure, metal, and chemistry. They were working with atomic nuclei, with fission, with neutrons, with chain reactions, with energies that, until then, had belonged mainly to stars and the hidden structure of atoms. And when scientists approach a new power for the first time, they must ask not only what they expect to happen, they must ask what could happen, even the unlikely, even the frightening, even the almost unimaginable. So tonight, we will move slowly through the story of that fear. We will not tell it as a fantasy. We will not pretend the scientists truly believed the Earth was likely to be destroyed. They did not. But for a time before the first test, the possibility of atmospheric ignition was considered seriously enough to calculate. And those calculations became one of the strangest footnotes in the history of science. A moment when the world did not almost end, but when scientists paused long enough to ask whether it could. To understand the fear, we must begin with the chain reaction itself. Before the atomic bomb, the most powerful explosions human beings had made were chemical. Gunpowder, dynamite, TNT, conventional explosives. These all release energy by rearranging atoms. Chemical bonds break and form. Electrons shift. Molecules transform. Energy is released as heat, pressure, and expanding gas. But the atomic bomb was different. It did not get its power from the outer electrons of atoms. It reached into the nucleus. The nucleus is the dense center of the atom, where protons and neutrons are bound together. In certain heavy atoms, such as uranium-235 or plutonium-239, the nucleus can split apart when struck by a neutron. This process is called fission. When a heavy nucleus fissions, it breaks into smaller nuclei, releases energy, and also releases more neutrons. Those neutrons can strike other nuclei. Those nuclei can split. They release more neutrons. And those neutrons can split still more nuclei. This is the chain reaction. One event becomes two become four become 8. If the material is arranged in the right way, if there is enough of it, if too many neutrons do not escape, the reaction grows incredibly fast. In a nuclear reactor, the chain reaction is controlled. In an atomic bomb, it is allowed to grow explosively for a tiny fraction of a second. The key phrase is critical mass. A nuclear chain reaction does not happen just because fissionable material exists. A small piece of uranium or plutonium does not automatically explode. The material must be brought into a condition where each fission, on average, causes at least one more fission before neutrons escape or are absorbed without continuing the reaction. If the chain reaction sustains itself, the system is critical. If it grows rapidly, it becomes supercritical. The bomb designers at Los Alamos had to arrange plutonium so that it would become supercritical almost instantly. In the Trinity device, conventional explosives surrounded a plutonium core. When detonated with extreme precision, these explosives compressed the plutonium inward. The density increased, neutrons were introduced. The chain reaction began. In less time than the blink of an eye, energy poured out. This was the known danger. A huge explosion, radiation, fallout, heat, blast, a weapon powerful enough to destroy a city. But there was another question, more theoretical and more cosmic. What if the chain reaction did not stop inside the bomb? What if the heat of the explosion caused the nuclei in the surrounding air to react? Air is mostly nitrogen and oxygen. These are not fission fuels. They are not uranium. They are not plutonium. They do not split easily and release more neutrons in a growing chain reaction. But at extremely high temperatures, nuclei can sometimes fuse. Fusion is the process that powers stars. Light nuclei combine into heavier nuclei, releasing energy if the reaction is favorable. The fear was not that the air would undergo fission. It was that the bomb might create a temperature high enough to start nuclear fusion reactions among nuclei in the atmosphere, especially nitrogen. If nitrogen nuclei could react with each other and release enough energy, and if that energy could heat nearby nitrogen enough to make it react too, then a propagating nuclear burn might be imagined. A chain reaction in the air, a nuclear fire moving through the atmosphere. That was the nightmare. But a nightmare is not the same as a physical possibility. To become real, the reaction would need to satisfy strict conditions. It would need to release enough energy. The energy would need to stay in the right place. It would need to heat neighboring air before escaping. The reaction rate would need to overcome losses. The nuclei would need to collide with enough energy to get through their electric repulsion. And the process would need to continue from one region of air to the next. This is not easy. Atomic nuclei are positively charged. They repel one another. To fuse, they must come very close together, close enough for the strong nuclear force to bind them. But because of their electric repulsion, they need enormous energy to approach that closely. In stars, gravity compresses and heats vast amounts of plasma for immense periods of time. The sun does not burn because a single spark ignited it. It burns because its core is massive, dense, and hot enough to sustain fusion over billions of years. An atomic bomb is hot, but it is also brief. The fireball expands, energy spreads, radiation escapes, the density of the air falls as the blast grows. The conditions do not remain like the core of a star, and this difference matters. A bomb can create astonishing temperatures for a moment, but it cannot hold the entire atmosphere in a compressed, star-like state. The atmosphere is not a bomb core. It is thin by nuclear standards. It is not confined by gravity strong enough to sustain fusion. It loses energy too quickly. This is why the calculations mattered. The scientists had to compare energy production with energy loss. If nuclear reactions in air produced energy faster than that energy escaped, the temperature could rise and the reaction might spread. If energy escaped faster than it was produced, the reaction would die. The Los Alamos calculations showed that the losses were overwhelming. The atmosphere could not sustain the reaction. The bomb would produce a fireball, but not a global fire. The chain reaction would stop. The air would not burn. Still, before the first test, the question lingered in the minds of some of the people involved. The Manhattan Project had gathered some of the greatest physicists of the 20th century. J. Robert Oppenheimer directed Los Alamos. Hans Bethe led the theoretical division. Edward Teller, who would later become known for his role in the development of the hydrogen bomb, was among the physicists thinking about nuclear reactions at extremely high temperatures. Enrico Fermi, brilliant and playful even in grim circumstances, was there too. The project was born out of fear that Nazi Germany might build an atomic bomb first. By 1945, Germany had surrendered, but the war in the Pacific continued. The United States was preparing to test a weapon whose power had been estimated but never seen. Uncertainty surrounded the test. Would the plutonium implosion design work? Would the explosive lenses compress the core symmetrically enough? Would the device fizzle? Would it release the expected amount of energy? Would the instrumentation survive long enough to record useful data? Would the radioactive cloud drift safely? Would the explosion be too small? Would it be too large? Would something unexpected happen? The atmospheric ignition question belonged to this larger cloud of uncertainty. It was not the main practical worry by the day of the test. By then, calculations had ruled it out as a real danger. The more immediate concerns were whether the bomb would work, how much energy it would release, and how to manage radioactive fallout. But the story of atmospheric ignition survived because it captured the mood of the age. The scientists were not merely building a bigger bomb. They were stepping across a threshold. The first nuclear explosion was an experiment in the deepest sense. It tested not only engineering but reality itself. It asked whether the equations were right, whether the materials would behave as expected, whether the new physics would remain contained inside the device. The idea of igniting the atmosphere was frightening because it transformed a weapon test into a cosmic question. Could a human-made reaction spread into nature itself? Could the boundary between controlled experiment and planetary catastrophe fail? The answer was no, but even asking the question revealed the scale of what humanity had entered. Let us imagine the desert, not as a battlefield, but as a waiting place. The Jornada del Muerto, the journey of death, a remote stretch of New Mexico chosen for isolation, flat terrain, and military control. In the darkness before dawn, the tower stood at ground zero. At the top was the gadget, a steel and explosive assembly containing the plutonium core. Miles away, observers waited in bunkers and at base camp. Some lay on the ground with their backs turned, as instructed. Some wore dark goggles. Some prepared instruments. Some expected success. Some feared failure. Some wondered what the blast would look like. No one on Earth had seen what they were about to see. There had been large explosions before. There had been war. There had been firestorms. There had been artillery, bombs, and chemical blasts. But this was different. A piece of matter would be converted into energy on a scale ordinary chemistry could not approach. The device was scheduled to detonate at 5:30 in the morning. The sky was still dark. The desert was quiet. The scientists waited for the countdown. And in that silence, the atmospheric fear became almost symbolic. It is said that Enrico Fermi, in a characteristically dark joke, offered wagers on whether the test would ignite the atmosphere, and whether it would destroy only New Mexico or the entire world. The joke frightened some people who did not know the calculations. Test director Kenneth Bainbridge was reportedly angry at Fermi for alarming the guards. This moment has often been retold, sometimes exaggerated, sometimes transformed into the claim that the scientists believed there was a real chance the world would end. That is not accurate. The calculations had shown that the atmosphere would not ignite, but Fermi's joke worked because the question had existed, and because everyone knew they were watching something unprecedented. Fear and humor often live close together at the edge of the unknown. Fermi understood the physics. He knew the world was not likely to burn. But the joke gave voice to the terrible absurdity of the situation. Humanity had built a bomb so new that people could joke nervously about whether it might ignite the sky. The actual science was colder and calmer. The atmosphere is mostly nitrogen, with oxygen and smaller amounts of argon, carbon dioxide, water vapor, and other gases. Nitrogen nuclei are stable. Oxygen nuclei are stable. They are not arranged like uranium or plutonium. They do not release neutrons in a branching fission chain. To make nitrogen nuclei react with one another, one must overcome strong electric repulsion. The reaction rates at bomb-produced conditions are far too low. The energy loss mechanisms are far too strong. The fireball loses energy by expansion and radiation. The hot region does not remain compressed. The heat spreads and weakens. The reaction cannot propagate. Even under deliberately pessimistic assumptions, where the dangers were exaggerated in the calculation to be safe, the conclusion was that atmospheric ignition was impossible. The same logic applied to the oceans. Another version of the fear imagined hydrogen in seawater fusing. Water contains hydrogen, and hydrogen fusion powers stars. But ordinary hydrogen in Earth's oceans is not sitting under stellar core conditions. The ocean is not compressed by the mass of a star. A bomb cannot turn the sea into the sun. The energy disperses. The conditions vanish. No self-sustaining fusion wave can travel through water. The universe does not burn just because a small region becomes hot for a moment. Fusion requires not only temperature but density, confinement, reaction rate, and time. Stars have these conditions. Bombs briefly create extreme temperatures, but not in a way that can ignite the planet. This is an important lesson. Words like hot and powerful can mislead us. The fireball of a nuclear bomb is hotter than the surface of the sun, but the surface of the sun is not where the sun's fusion is powered. Fusion occurs in the core, where the pressure and density are enormous and where gravity confines the plasma. A nuclear explosion is hotter than many familiar things, but it is not a star. It is a rapidly expanding blast. For a chain reaction to spread, heat must not simply exist, it must be sustained, it must be transferred efficiently. It must create more reaction faster than energy is lost. The atmosphere fails this test. The world is safe from that particular nightmare. Not safe from nuclear weapons, not safe from fallout, not safe from war, not safe from human decisions, but safe from the atmosphere itself becoming fuel. And this distinction is the heart of the documentary. The atomic bomb did not threaten to destroy the world by accidentally igniting the sky. It threatened the world in another way, through power, through politics, through war, through fear, through the possibility that human beings would use nuclear weapons again and again. The real chain reaction was not in the nitrogen of the atmosphere. It was in history. One bomb led to a test. The test led to Hiroshima, then Nagasaki. Then the end of one war and the beginning of another kind of war. A Cold War, an arms race, hydrogen bombs, intercontinental missiles, submarines, bombers, fallout shelters, doomsday planning. The real world-ending danger was not a single physical ignition in 1945. It was the continuing human ability to build, stockpile, and possibly use weapons powerful enough to devastate civilization. The atmosphere did not burn, but the nuclear age began. Let us return to the Trinity site. The countdown reached its end. At 5:03 a.m., the device detonated. For an instant, night became brighter than day. A fireball formed where the tower had been. The explosion lit the desert, the mountains, and the faces of observers miles away. Heat washed over them. The shock wave arrived later. The tower vanished. The sand below melted into a greenish glass later called Trinitite. A mushroom cloud rose into the sky. The world had not ended, but the world had changed. Some observers were stunned into silence. Some felt awe. Some felt relief. Some felt dread. Kenneth Bainbridge is remembered for saying to Oppenheimer after the test that now they were all sons of bitches. It was not a scientific statement. It was a moral one. The test had worked. The physics was right. The weapon was real. Human beings had done it. The atmosphere remained overhead, ordinary and impossible to burn in the way once feared. The sky did not become nuclear flame. The oceans did not ignite. The planet continued turning. But the knowledge could not be undone. The first atomic bomb test was not merely the proof of a theory. It was the crossing of a line. After Trinity, no one could pretend nuclear weapons were only a possibility. They existed. They worked. They could be made again. The scientists had spent years racing to solve the physics. Now, the physics had become history, and history would not stop at the test tower. The story of the atmospheric ignition fear is often told because it seems to offer a simple kind of suspense. They might have destroyed the world. They pushed the button anyway. But that version is too simple. It makes the scientists look reckless in a way that misses the real complexity. They did not ignore the risk. They calculated it. They argued about it. They examined the nuclear reactions that might matter. They compared energy gained and energy lost. They concluded that the runaway reaction could not happen. That is what responsible science does when faced with a frightening possibility. It does not laugh it away. It does not believe it because it is dramatic. It calculates. And if the calculation is uncertain, it pushes assumptions toward danger to see whether the conclusion still holds. In the Los Alamos report, the authors deliberately considered dangerous assumptions. They looked at the most concerning atmospheric reactions. They asked whether energy from nuclear reactions could overcome radiative losses. They concluded that even if bombs far larger than those under consideration were used, the processes of energy loss would prevent a chain reaction in air. This did not make nuclear weapons safe. It made one particular apocalypse impossible, and that is the correct balance. The myth is wrong if it says the scientists knowingly risked a significant chance of burning the world. But the myth points to something true if it says the first atomic bomb forced scientists to think about consequences at a planetary scale. Before nuclear weapons, most human technologies were local or regional in their immediate destructive power. A cannon could destroy a wall. A bomb could destroy a building. An army could destroy a city. Industrial civilization could alter landscapes. But nuclear weapons introduced a new scale of instant destruction. The Trinity test did not ignite the atmosphere, but it proved that matter itself could be used as a weapon. And when humanity learned that, the meaning of war changed. This is why the story remains unsettling. The frightening part is not that the calculations were wrong. They were right. The frightening part is that human beings had reached a level of power where such calculations became necessary. Imagine being one of the physicists. You spend your life studying nuclei, particles, equations, scattering, energy levels, quantum behavior. The work is abstract, elegant, difficult, often far removed from ordinary experience. Then war comes, fear comes. A secret laboratory is built on a mesa. The abstractions become machines. The equations become explosive lenses, neutron initiators, critical masses, and blast estimates. Then someone asks whether the atmosphere might ignite. You know it sounds absurd, but you cannot answer only with intuition. The stakes are too high. So you calculate. You look at nitrogen, oxygen, reaction cross-sections, energy release, radiation loss, thermal equilibrium, propagation. You ask if a temperature exists at which energy production balances energy loss. You ask if a heated region of air could maintain itself. You ask if the reaction products would carry energy forward. You ask if radiation would drain the heat away. And the answer comes back: no. The losses win. The air will not burn. The bomb will explode, and then the fireball will expand, cool, and die. That is the scientific answer. But the emotional answer remains. What kind of world requires this calculation? The scientists of Los Alamos were not all the same. Some were driven by fear of Hitler, some by patriotism, some by scientific ambition, some by duty, some by curiosity. Some later regretted their work, some defended it, some campaigned for arms control, some continued into the hydrogen bomb program, some changed their views as the war ended and the Cold War began. There is no single mind of the Manhattan Project. There were many minds. Brilliant, flawed, afraid, ambitious, human. The atmospheric ignition story touches them all because it stands at the intersection of knowledge and consequence. The scientists had to think like physicists, but they also had to live as people inside history. One of the central figures was Hans Bethe. Bethe was one of the great theoretical physicists of the 20th century. Before the war, he had worked on the nuclear processes that power stars. He understood fusion, energy generation, and stellar interiors. This made him especially relevant to the question of whether a nuclear explosion could ignite atmospheric fusion reactions. If anyone could evaluate such a danger, it was someone who understood how nuclear fire works in stars. And the answer was clear. The atmosphere is not a star. A bomb is not a stellar core. The reaction would not propagate. Edward Teller is also central to the story. Teller was fascinated by thermonuclear reactions, the processes that would later lead to the hydrogen bomb. He was among those who raised or explored the question of atmospheric ignition. In later years, his name would be linked to far larger nuclear weapons, weapons that used fusion fuel to release energies dwarfing the fission bombs of 1945. The fear of atmospheric ignition sits strangely beside the later development of the hydrogen bomb. In 1945, scientists asked whether a fission bomb might accidentally trigger fusion in air. Later, scientists deliberately designed weapons to trigger fusion in bomb fuel. But fusion in a weapon is not fusion of the atmosphere. A hydrogen bomb uses carefully arranged conditions, fission primaries, fusion fuels, radiation compression, and weapon geometry. It is a designed system. The atmosphere is not such a system. It is not dense enough, not confined enough, not reactive enough. Again, the distinction matters. A nuclear weapon can be unimaginably destructive without being able to ignite the world. The myth persists because the image is powerful, the sky catching fire, the oceans burning. A test in the desert becoming the end of life. It sounds like an ancient warning. Prometheus stealing fire, humanity touching the power of the sun, a forbidden experiment, a question whispered before dawn. But the real story is more subtle and, in some ways, more disturbing. The scientists did not almost destroy the planet by accident. They created a weapon that made deliberate destruction possible on a scale never before seen. The danger moved from physics to politics, from nitrogen nuclei to human choices. From one impossible chain reaction to another, very possible one: arms race, retaliation, escalation, miscommunication, fear. The atmosphere could not become a nuclear fuel, but nations could become locked into a chain reaction of suspicion. One weapon leads to another. One test leads to another. One stockpile leads to another. One doctrine leads to another. This is the chain reaction that mattered, and unlike atmospheric ignition, it was not physically impossible. It happened. After Trinity, nuclear weapons grew more powerful. The first atomic bombs were devastating. Later, thermonuclear weapons became vastly more destructive. Tests moved from deserts to islands, from towers to aircraft, from underground shafts to remote sites. Fallout spread. Communities were exposed. Landscapes were contaminated. The world learned new words: megaton, fallout, deterrence, mutual assured destruction, doomsday. The atmosphere did not ignite in 1945, but the imagination of the world did. Humanity began to live under a new kind of sky. A sky that looked the same, but now existed above cities that could be destroyed in minutes. This is why the Trinity story still has power for a sleep documentary, even though it is dark. It is not only about fear, it is about the silence before knowledge becomes irreversible. The night before the test. the calculation before the fire, the moment when the world is still the old world, but only for a few more minutes. There is something haunting about thresholds, a door before it opens, a match before it strikes, a countdown before zero. Trinity was such a threshold. The scientists waited in the dark, surrounded by instruments, wires, bunkers, desert scrub, and the memory of equations. Above them was the same atmosphere that had covered Earth for billions of years: nitrogen, oxygen, clouds, winds, weather. The same sky under which oceans formed, life evolved, civilizations rose, and wars began. The question had been asked: could this sky burn? No. But could the world change forever beneath it? Yes. At 5:30 a.m. it did. Let us look more closely at why the chain reaction inside the bomb was so different from the imagined chain reaction in air. Inside the bomb, the fuel was chosen because it was fissile. Plutonium-239 can sustain a chain reaction when arranged correctly. When a neutron enters the nucleus can split, releasing energy and more neutrons. Those neutrons can continue the reaction. The material is dense. The geometry is designed. The timing is precise. The bomb briefly creates a supercritical configuration, and the reaction grows exponentially. Air has none of those properties. Nitrogen and oxygen are light, stable nuclei. They are spread thinly as gas. They do not fission into more neutron-producing fragments. Fusion between nitrogen nuclei would require overcoming large electric repulsion. The products would not create a branching chain like neutrons in plutonium. Energy would be lost rapidly to radiation and expansion. The reaction cannot feed itself. A forest fire spreads because burning wood heats nearby, wood to ignition. The fuel is dense enough, oxygen is present, heat transfer is effective enough. The chemical reaction continues. Atmospheric nuclear ignition would require something analogous at the nuclear level. But the conditions fail. The fuel is wrong, the density is too low, the heat escapes, the reaction rate is too small. There is no self-sustaining burn. The fireball from Trinity was real, but finite. It grew, it shone, it cooled, it became a cloud. The atmosphere survived because physics made it survive. This conclusion was not based on wishful thinking. It came from comparing the numbers. The scientists were able to show that the energy losses would prevent the atmosphere from reaching or maintaining any runaway state. In the most dangerous imagined reactions, the energy produced was not enough to overcome the ways the hot air would shed energy. Even under exaggerated assumptions, the chain reaction failed. That is why Trinity proceeded. Not because the scientists accepted a real chance of ending the world, but because the danger had been analyzed and ruled out. The difference between an unknown risk and a ruled-out risk is important. Science cannot remove all danger from a weapon test, but it can distinguish between real and unreal mechanisms. Fallout was real, blast was real, heat was real, radiation was real, atmospheric ignition was not. The tragedy of nuclear weapons lies in the real dangers, not the impossible one. This also teaches us something about myths. A myth can survive even after the facts are clear because it expresses a feeling. The atmospheric ignition myth expresses the feeling that nuclear weapons are unnatural, cosmic, and almost forbidden. It turns anxiety into an image. The sky burning is easier to picture than geopolitical instability, radiation exposure, arms control treaties, and decades of deterrence. It is one dramatic image instead of a long human problem. But good history must separate image from reality. The image is powerful. The reality is more important. And the reality is that careful scientists asked a terrifying question, calculated it, and found that nature would not allow that particular catastrophe. Then humanity created other catastrophes by choice. As the Trinity fireball faded, no one yet knew exactly how the nuclear age would unfold. They knew the test had succeeded. They knew the weapon could be used. They knew the war was still ongoing. They knew secrecy surrounded everything. But they did not yet know the full future. They did not know the Cold War in detail. They did not know the Cuban Missile Crisis. They did not know the thousands of nuclear warheads that would one day exist. They did not know the generations of children who would practice hiding under desks. They did not know the treaties, protests, near misses, accidents, and arguments that would follow. They did not know that people many decades later would still be telling the story of the question that came before the first blast. Could it ignite the atmosphere? In one sense, the story is over quickly. The calculation says no, the bomb detonates, the world remains. But in another sense, the story never ended. Because every powerful technology brings its own version of the same question. What if this spreads beyond our control? What if the system behaves differently than expected? What if the consequences are larger than the experiment? What if the chain reaction is not only physical, but social, political, ecological, or moral? The atomic bomb was one of the first technologies to force this question at a planetary scale. Today, other technologies raise different versions of it: climate engineering, artificial intelligence, biotechnology, high-energy physics, autonomous weapons, synthetic organisms, global networks. Not because they are the same as nuclear bombs, they are not, but because they remind us that technical power grows faster than wisdom unless wisdom is deliberately cultivated. The Trinity scientists had to calculate whether the sky could burn. We must keep asking what our own chain reactions might be. Some fears are exaggerated, some are physically impossible, some are real. The challenge is knowing which is which. That is why the atmospheric ignition story remains useful. It shows both imagination and discipline. The scientists imagined the worst. Then they tested the idea with physics. They did not accept terror as evidence. They did not accept reassurance as evidence either. They calculated. And when the calculation showed impossibility, they moved on to the dangers that were real. That is the responsible path. Fear alone is not enough. Dismissal alone is not enough. Evidence must decide. Still, when we imagine the morning of July 16, 1945, we can understand why the fear felt emotionally real. The device on the tower contained only a small amount of material compared with the size of the world, yet it was expected to release an enormous amount of energy. This is one of the strange truths of nuclear physics. Most of the atom's mass energy remains locked away, but even a tiny fraction released can be devastating. The atomic nucleus is so compact, so deeply bound, that changes within it can dwarf chemical reactions. Before Einstein and nuclear physics, mass and energy seemed separate. Afterward, matter itself became a reservoir. The bomb did not convert all its mass into energy. Only a tiny fraction became explosive energy. But that tiny fraction was enough to create a blast equivalent to thousands of tons of TNT. This is what made the device feel almost unreal. A small core, a tower, a desert, a force greater than any conventional bomb, a fireball brighter than dawn. It is easy to see how the mind could leap from enormous to unlimited. But physics lives in limits. The atmosphere could not carry the reaction because the necessary conditions were absent. The bomb was powerful, but not magical. Nuclear physics is not sorcery. It is governed by probabilities, forces, energies, barriers, losses, and conservation laws. The world did not burn because the numbers did not permit it. This is also why the story should not be told as if the scientists were fools. They were not foolish for asking. They would have been foolish not to ask. When you are about to create the first nuclear explosion in history, you examine even strange possibilities. A question can be frightening and still be scientifically responsible. In fact, the frightening questions are sometimes the most important ones to ask early, before the test, before the deployment, before the irreversible act. The atmospheric ignition calculation belongs to that category. It was a pre-dawn question. A question asked before the first fire, and because it was asked, it could be answered. Let us imagine the calculation not as equations on a page, but as a balance. On one side, energy production. Nitrogen nuclei reacting at extreme temperature, releasing energy into particles. On the other side, energy loss. Radiation escaping, electrons carrying energy away, the hot air expanding, the fireball cooling. For ignition, production would need to exceed loss. The balance would need to tip toward runaway heating. But it did not. Losses dominated. Energy escaped too efficiently. The atmosphere was too transparent, too diffuse, too stable. The nuclear reactions were too rare. The chain could not move outward. The balance tipped towards safety, not total safety, but safety from global atmospheric fire. The bomb could still kill. The bomb could still contaminate. The bomb could still change history. But it could not turn the sky into a star. That sentence captures the physics. A bomb cannot turn the sky into a star. The sun is held together by gravity. Its core is under immense pressure. Its fusion is slow and sustained. The atmosphere of Earth is a thin shell around a small rocky planet. It is not compressed, it is not confined, it is not made of the right fuel in the right conditions. The desert fireball was brief. The sun is continuous. The difference is everything. The fear of ocean ignition has a similar answer. The oceans contain hydrogen, but not under the conditions needed for runaway fusion. Water is dense compared with air, but not remotely like a stellar core. The hydrogen in ordinary water is mostly protium, not the fusion fuel mixture of a thermonuclear weapon. The energy from a bomb dissipates. It cannot confine and heat a global ocean into nuclear burning. The oceans were never going to burn. But again, the question had emotional power. Air and water are the two great elements of life. To imagine them igniting is to imagine the world turning against itself. Sky as fuel, ocean as fuel, earth as bomb. No wonder the story survived. But the true danger of nuclear weapons never required the whole atmosphere to burn. A city can be destroyed without the world ending. A population can suffer without the oceans igniting. Radiation can harm generations without a global fire. Human civilization can be threatened by many detonations, by escalation, by fallout, by nuclear winter scenarios, by infrastructure collapse, by political failure. The impossible apocalypse should not distract from the possible ones. This is why a documentary on this topic should end, not with relief alone, but with reflection. The relief is real. The atmosphere could not ignite. The scientists knew enough to rule it out. The world was not one button away from accidental physical annihilation. But the unease is also real. Because Trinity proved that human beings could release nuclear energy in war, it showed that the boundary between theoretical physics and world history had disappeared. After Trinity, the atom was no longer only a subject of research, it was a weapon. And the question changed. Not, can the atmosphere burn, but what will humans do now? The first question had a clean physical answer. The second did not. Physics could calculate nitrogen reactions. It could not calculate conscience. It could estimate blast yield. It could not decide whether a weapon should be used. It could model energy loss. It could not guarantee wisdom. This divide between knowledge and wisdom is one of the deepest themes of the atomic age. The Manhattan Project was a triumph of science and engineering. It was also the beginning of a moral burden that is never fully lifted. The scientists solved the problem they were given. Then the world inherited the consequences. Some of them later argued for international control of nuclear energy. Some warned against arms races. Some supported further weapons development. Some regretted. Some defended. Some remained conflicted. That complexity is part of the truth. No simple story can hold them all. But the atmospheric ignition fear gives us one clear scene. Before dawn, before the first blast, people waited under a sky they had calculated would not burn. The sky remained. The bomb worked, the age changed. Imagine the desert after the explosion. The fireball gone, the cloud rising, the sand transformed, the tower erased. The instruments recording. The observers emerging from bunkers and shelters. The air still air. The sky still sky. The world still turning. From a distance, dawn began like any other dawn. Light spread across the desert. Mountains took shape. Shadows shortened. Birds, if any were nearby, would have known nothing of fission, plutonium, or geopolitics. The Earth continued. But human history had been marked. There was now a before Trinity and an after Trinity. Before, nuclear weapons were theoretical. After, they were real. Before, the chain reaction had lived in calculations in laboratories. After, it had lit the desert. Before, the fear of atmospheric ignition could still belong to imagination. After, it was replaced by something more concrete. The weapon had not destroyed the world. It had entered it. And sometimes that is more frightening. A mythical catastrophe happens once and ends everything. A real technology remains, spreads, improves, and waits. The bomb did not start a chain reaction in the atmosphere. It started a chain reaction in human affairs. That is the haunting truth. One test led to more tests. One weapon design led to another. One nation's bomb led another nation to build its own. The logic of deterrence became a kind of equation too. If they have one, we need one. If they build more, we build more. If they can strike, we must be able to strike back. Fear produced weapons. Weapons produced fear. A chain reaction, but not nuclear in the air. Political in the mind. Strategic in governments. Industrial in factories. Psychological in populations. This chain reaction did not violate physics. It followed human logic, and it proved much harder to stop. This is why the story is still worth telling calmly at night without sensationalism. Because calm allows us to see the real shape. The world was not nearly burned by nitrogen fusion, but it was changed by nuclear fission. The scientists did not press a button while believing Earth might likely ignite, but they did press a button that opened a new era. The frightening calculation was not the end of responsibility. It was the beginning. As we rest with this story, we can hold two truths at once. The first is reassuring. The first atomic bomb could not have ignited the atmosphere. The physics was checked. The reaction could not sustain itself. The sky was never going to burn. The second is sobering. The bomb did not need to ignite the atmosphere to become one of the most consequential inventions in human history. Sometimes the impossible fear is not the real danger. Sometimes the real danger is what remains after the impossible fear is gone. That morning, the impossible did not happen. The possible did. A nuclear weapon exploded. The desert flashed brighter than sunrise. A new form of power entered the world. And the question that remained was no longer whether nature would run away from us. It was whether we could control ourselves. This is the quiet center of the Trinity story. The atmosphere was safe from ignition. Human history was not safe from escalation. The sky would not burn. But cities could. The oceans would not fuse. But nations could threaten each other with weapons capable of unimaginable destruction. The planet would not be destroyed by one accidental chain reaction. But civilization could still be endangered by deliberate choices. The scientists had answered the physics question. The moral question remained open. And perhaps it still remains open. Today, the Trinity site is a historical place. The tower is gone. The desert has changed. Fragments of trinitite remain as reminders of the heat. Visitors can stand near where the first nuclear fireball rose. They can look at the sky and know that it did not burn. They can look at the ground and know that something irreversible happened there. A test site is a strange kind of monument. It is not a battlefield in the traditional sense. No armies clashed there, no city stood there, no enemy was present. And yet it marks one of the most important moments in the history of war. It is a place where theory became weapon, where calculation became flash, where the atom became political, where a fear of burning the world gave way to the reality of a world armed with nuclear fire. The desert remembers in silence. The wind moves over the ground. The sky remains blue. At night, stars appear over New Mexico, the same stars whose fusion once helped scientists understand why the atmosphere would not ignite. The stars burn because they are massive, dense, and confined by gravity. Earth's air does not burn because it is none of those things. The stars are nuclear furnaces. The atmosphere is not. That simple fact saved the world from one imagined catastrophe. But it did not save the world from the age that followed. And so the story ends not with panic, but with a quieter kind of awe. There was a moment when scientists looked at the most destructive device ever built and asked whether it might awaken a reaction in the sky. They checked the laws of nature. They found the sky would hold. Then they detonated the bomb. The sky held, the earth held. The desert did not. The tower vanished. The sand melted. The cloud rose. The nuclear age began. And from that morning onward, humanity lived with a new knowledge. The world was not fragile in the way the myth imagined. The atmosphere could not be lit like paper. The oceans could not be turned into flame. But civilization was fragile in another way. Fragile because knowledge can become weapon. Fragile because fear can multiply. Fragile because power can outrun wisdom. Fragile because the most dangerous chain reactions do not always happen in atoms. Sometimes they happen in decisions, in governments, in wars, in the stories nations tell themselves, in the belief that safety can be built from terror alone. Tonight, as the world outside grows quiet, we can let the desert fade, the tower, the wires, the bunkers, the countdown, the flash, the cloud, the question. Could the bomb ignite the atmosphere? No, but it ignited the nuclear age. And that was more than enough to change the world. The atmosphere remained above the desert, calm, transparent, unburned. The stars remained far away. The oceans remained dark and heavy under the moon. The planet continued its slow turning. But somewhere in human history a door had opened, and beyond that door was not the end of the world in one instant. It was something longer, a new responsibility, a new fear, a new kind of power, a new need for restraint. The first atomic bomb did not set fire to the sky. It illuminated the future, and what it showed was both brilliant and terrible. A world that had survived the test, and a humanity that would have to learn how to survive itself.